Hi, I'd like to talk about the problem password rotation from ACPC 2020, the Alberta Programming Contest. This is a good example problem for how to use string hashing. So in this problem, you were given a long list of compromised passwords, and in fact, there could be, I think, up to 100,000 of them. And on top of that, each password could be pretty long. It could be up to 500 million, rather 500,000, half a million characters long. Although there was a constraint that the sum of the lengths of all passwords will not exceed 1 million. And you were being asked if there's any two passwords in this list where one is a rotation or a reverse rotation of the other. And these rotations are formed by splitting the password somewhere and then uh, switching those two parts. So for example, if you had the password ABCD, then you could rotate the A to the end. It would be BCDA, and then you could do that again. So there would be CD AB, and then here you would find the rotation that occurs in that list as well, right? So in general, if you have a password here, you could split it somewhere into a left and right part, and then the rotated password would have the right part followed by the left part. So this here is what is meant by rotation. It was also possible that the password was first reversed. So, for example, here in this case, it may become um, DCBA, and then rotations of that could be found as well. Actually, I think in this case it was DBCA. The you see that um, this should be uh, no, sorry, this is the no case. Never mind. Looking at this case here. So like in this case, so if we split the if we reverted this DCBA, and so now we can rotate the D to the end, BCBAD. That's this one here. Okay, so this is a rotation, reverse rotation, and this one is actually the no case in terms of the output. Okay, so this is the problem. Okay, now let's understand how we use hashing to solve this problem, right? So hashing, the idea is that you have a string, let's say it's called a string s, and it consists of characters, let's say s0, s1, s2, s3, and maybe s4 in this case. So um, and you want to compute a number, a hash function h of s, and you want to do this in a deterministic way so that if two strings are the same, they have the same hash number. If they're not the same, then they may still have the same hash number, but we're going to try to make it so that this is rather unlikely. To do that, we pick a prime number, and call it p, okay? And we will be doing all operations within a modulus. So this prime number, call it p, and then we have a larger modulus m, and it's also prime number, so that we are operating in a field. Now, the idea for the hash function is this. Okay, so we start by we're going left to right, we're hashing s0. Okay, so the hash of s0 is actually it's just going to be s0. I'm going to we'll say this is basically the hash of if we just had the string as 0, right? So then the next thing is we'll be adding s0, we'll be adding s1 to it, okay? The way we do this is by multiplying s0 with p times s0 plus s1. So that's the string for the if we added s1. So now let's add the next thing. So then we multiply by p, so we get p squared s0 plus p times s1 plus s2. So this is the hash of this, and now the hash of this substring. And then I shouldn't say s, so this would be h, um, from s0, s1, s2, and then we'll say s 0 to S3, and here h of S0 to S4. And it works the same way. So we have p to the power of 3 S0 plus p squared S1 plus p S2 plus S3. And then this would be p to the power of 4 S0 plus p cubed S1 plus p squared S2 plus p times S3 plus S4. So these are easy to compute, as you can see, and we can compute those as we call prefix hashes in one loop, and we only remember all of these in a table. Now, why is that useful? First of all, this produces a low number of collisions for different values. But it has another advantage. It allows us to compute the hash value for any substring in constant time. Now to see that, okay, let's look at one example. Okay, what if I were asked to compute the hash value for the substring for this substring here, for this part? Okay, so in other words, what if I were asked to compute the hash value of S2, S3, and S4? If I just used this made this string here, right? Well, the answer clearly should be something like this, right here in this case. So the answer should be p squared times S2 plus p times S3 plus S4. Right? This is what I want to compute. Can I do that by using those pre-computed values in this case? Okay, and the answer is that I can. Okay, so if you look at this, right, what you can do is you can take this value here, okay, and you can subtract, and here so this value has an extra S0 and S1, and you can simply subtract this value here. If you take this value and you first multiply it by what? By p to the power of 3. Okay, so if I take, so in other words, I can say that a s of S2, S3, and S4, okay, so for this string is equal to h of, in this case, the entire string S0 to S4, okay, minus, and then I can say p to the power of 3 times h of S0, S1. Okay? And both this and this, those are values that I've pre-computed in my prefix table in this case. So that is the idea, and the same is really true for any substring. I can take any substring here, and it can compute its hash by simply taking the hash of where the substring ends here, and subtracting from it the an earlier hash by shifting and multiplying this earlier hash with the corresponding power, right? So if we multiply this here with if you multiply this expression here with the power of 3, we get exactly the part that we need to cancel out to obtain this. So the now for this particular problem, we're looking at rotations. So okay, let's take a look, understand how this will work. Okay, so we're basically being asked to compute the hash of a rotation, and the way to think of it is that the rotation here has maybe this string is split into a left and a right part. We're asking what, and then as we rotate it, we're basically exchanging left and right. And so to do that, we basically have to compute the hash of this right, followed by left. And so what is that? Okay, so this is the hash of right here in this case. Okay, this is this part here. Okay, needs to be multiplied by, okay, our p to some power, okay, plus the hash on the left, right? So this hash here is already the one part, but the this part here needs to be shifted to basically to the left, and this x here, the number to shift it by, that is basically the length of L. Okay. So this is the formula that we need to compute, and this allows us to determine the hash of all the rotations in constant time. Okay, so let me show you how to use the library that Peter Steele created for our programming team, so that we can um, you can see how to actually code this. Okay, so to that end, I have already started and created a starter code with a fast scanner, and the first thing we need to read is then the number of strings that are in the input, and then we'll be reading each of these strings. I'm going to call them word, short for password. Okay, so this is the next thing that we need to read. So we need to compute these hashes. But actually, at this point we would need to check if this word is a hash or is equal to a hash of an already read word. I'm going to show you that in a minute. So let's look at how to compute the hashes for all the rotations. So say compute and store the hashes of all rotations. Okay, of this one. Right. I'll call this a function. We'll say add hashes for this particular word. And you see in a second why I write a function for this rather than just inlining it. Okay, so I'm going to say add hashes, and the hashes for this word is what I want to compute. Now here I need to consider all possible ways in which to split the um, this word. So, oops. So all possible hashes. So in other words, I have to split the string here at some point. We'll call it at index j. So from 0 to j, this is will be my L part, and then from j to the end, this is going to be the R part. Okay? So let's do that by, first of all, we need to build a hash structure to compute those prefixes, right? So let's compute this hash structure. I'm going to call it H. This comes from our library. It's easy to use. We just say we want a new hash structure with this word. And then we'll need to look at all possible ways, let's say call it J, of splitting the string into two halves, okay? That goes, so J from 0 to word dot length, okay? So now we're splitting basically from 0 to h, and from 0 to h, that's our L, and the R part is from j to basically the end. Right? So I need to obtain the hashes of both of these. Okay, so the hash, I'm calling it L. That is the hash, and now this hash implementation that we have here is shown on the right, and it has a function called get substring hash, shown here on the right. And I can use this function and say get substring hash from 0 to j, this is 1, and the right one is the substring hash from j to the end, and that is in this case word dot length. And now I need to combine the two. Okay, and to combine this, I'm going to call this this hash value h. I now need to take r, and I need to multiply it with really this p to the power of j, okay, and then plus l. Now to do this operation here, I need to do this operation in the in that ring. Say so logically, this is what I want to do. The way I code this here is by using a function that is provided by the hash function. It's called modulo multiply. So I could, in this case, the reason this is being used is for efficiency reason. I'll explain that at the end. So I'm going to multiply r with, and then p to the power of j. The hash structure actually has a cache, and in this cache I can just look at and grab the kth power. So I'm going to take this, multiply this, okay, and then to this I will be adding L, and I also got to make sure that that this is a positive number. So I'm going to mod this I'm going to first add h prime to it, and then mod this. Okay, so the reason this is necessary here is because this product here is can be negative, but I want to make sure that this hash value h here is positive, so that I don't inadvertently mistake things to be different just because one has a positive and the other one has a negative sign. So this hash value h is the hash value of this particular rotation, and now I need to add it. Right now I'm going to add it, and I'm going to have a function I'm going to call it hashes. I'm going to add this here. And so this will be a global variable. So I'm going to use a hash set. I'm going to call it hashes, in which I will be storing these hashes. Okay. So let's see if that compiles. It does. Now, I said the reason why I'm writing a function add hashes is that we also need to look at reverse rotations. Okay, so I'm going to reverse this string here, and I'm going to do the same process for those reverse rotations. Okay, so the string reversed is the reverse string. I want to add the hashes of the reverse rotation here as well. So now that I've done that, now there's I'm ready to do the checking. Really, the next word that I'm reading here, I want to check really if the hashes that I've maintained so far contains the hash of this word. Right? So now the hash of this word, I'm going to call it maybe hash. Um, so if that's the case, right, then I'm going to need to report that yes, there's a conflict here, and we're done. And if that situation didn't occur to the end, then the answer here is no. So what is this hash that we want to compute? Well, for this hash here, we need to compute the hash that we obtained from those words. So this is really this, right? I have to compute the hash structure, and this would be the for the entire one. Now, because I have to do this here, right? I don't want to create two new hash structures, because creating the hash structure, I'm going to show you this here, actually goes through that process here. This is the constructor of building all these prefix hashes, and also this power cache here. So this is an O of n operation. I don't want to do that twice, and for that reason, I'm going to be changing the add hashes function here by passing this h to it, and so this will become a parameter, and we only assume that the caller has pre-computed the correct hash structure for this one. And now under this schema, I'm going to have to do this for the reverse one as well with the ref. Okay. Right. So let's see if that compiles, and if that works. The first input should be yes. Second yes. Third one should be no. So we're getting those answers here. Um, Let me submit this to the to Caddis to see if that works. So this works, and it was accepted. Right. So going back, how to to show this, we could use mostly our prepared code in this case, but we still have to understand how it works under the hood, so we could then compute the hash value that we obtain for those rotations. Right. So the last thing I want to mention earlier is why am I using modular multiply as opposed to just straight multiplication. Probably possible to use straight multiplication as well if we had chosen a different prime number. Our code chooses a rather large prime number. This is actually prime number here for the modulus m, right? The space is what I'd called earlier p, and this is the number that we are multiplying. So we're using a rather large one. This is to the order of 10 to the 16. And it is so large, in fact, that if we multiply two 64-bit numbers here, we would be overflowing, right? This would be a 10 to the 18. And so we would have to use big integer. But this modular multiply function here is efficient in that it can compute the modular product, so it's like p times q using some mod m, even if p and q are in that field of with a modulus of 10 to the 16 plus 61. this large prime number that Peter chose here. And the reason why he chose that is because the larger the prime number, the lower the probability of a collision. Okay, so here we have very, very low collision probability, and that makes it so that if we detect a collision here, in this case, we can just output and say, yes, it looks like we have a duplicate password, or one is a rotation of the other. Um, if you had chosen a smaller prime number, then there would be a high likelihood of collision. Now, I don't know if for this problem it might still have worked, it might not have worked, but this is the code that we have to do that. Note that it's possible for a malicious problem setter to always construct a test case that breaks a particular hashing function. To do that, they would need to know what our prime number, what our bases are, right? And the countermeasure here would be to choose, for example, the base randomly at runtime from some particular range. Now, I also want to point out that if there had been a need to add a check for collisions, that could have been done easily, right? So in this case, you would have not used a hash set, but you would have used a hash map, and you would have remembered for each of the hashes, which string or which rotation they correspond to. And then when a collision is collision here is detected, then so not a collision, but when a match is detected, then you would check whether the original strings in fact matched or not, and if not, then you just would keep going. Last comment I want to make about these hashing. So these hashes, so again, they have the property that we can have a large string, and we can compute the hash of any substring here in constant time. We can also do more. We can, for example, we can for example, find the longest common subsequence between two strings, right? By pre-computing the hashes for both of them, we can do a binary search over the length of that common substring, because it's possible for us to compute the hashes of all substrings of a given length very efficiently in linear time. So I can do that, say, well, for example, substring of length 3, say this is either this substring, or it is this one here, or it is this one here. Since all of these can be computed in O of 1, it is possible to get a list of all the hashes of substrings of a given length in linear time by doing one iteration. That makes it possible to include it into a binary search for a total complexity of O of n log n. So there are a number of problems where we can do this. Also, there are some problems where the items that are being hashed are not necessarily strings, but maybe other more complex things. And here the algorithm will still work, even if the different characters in that string are not actual characters, but maybe if they are integer numbers or long numbers.